we have this infinite sum, n over 2 to the power n times the product of a1 all the way up to an raised to the power of 1 over n. So we're trying to find out the maximum value of this infinite sum if, given that the infinite sum of an itself is equal to 1 and every term is non-negative. So in other words, what kind of non-negative sequence whose sum is 1? You can think of any. So what kind of such infinite sequence would give us the maximum value of this infinite sum? So naturally, the first thing we come up with is using AM-GM inequality. Say, n over 2 to the power of n times a1 times all the way to n to the power of 1 over n is less than or equal to n over 2 to the power of n times the sum of a1 all the way up to an over n. And so that's equal to a1 all the way to an over 2 to the power of n. Now, this infinite sum, in other words, is less than or equal to n from 1 to infinity, a1 an over n. So which means first term is with a1 over 1, second term is a1 plus a2 over 2, third term is a1 plus a2 plus a3 over 3, so on and so forth. Now, if that's the case, what can we say about this? Can we say about the maximum value is reached when every term is equal to each other? The a1 equal to a2 all the way up to equal to an. So what does that mean? Each term is equal to 1 over n. And we also have to satisfy this condition, that a1 plus a2 all the way to infinity is equal to 1. So that doesn't make a lot of sense to me. Plus, the question cannot be that straightforward. The solution cannot be that straightforward. So when we look at 2 to the power of n, maybe we can try, instead of a1 times a all the way to an, we can maybe insert 2 times a1 times 2 to the power of 2 times a2 all the way up to 2 to the power of n times an. Right? So that's less than or equal to raised to the power of 1 over n, less than or equal to 2a1 plus 2 to the power of 2 times a2 all the way 2 to the power of n an over n. And that is sigma k from 1 to n, 2 to the power of k times ak. K goes from 1 to n over n. And at the same time, that is equal to simplify this. So 2 times 2 to the power of 2 times 2 to the power of 3. So we have a common base of 2. So 2 to the power of 1 plus 2 plus 3 all the way up to n. We have the formula. That is half of n times n plus 1. Okay. Then we a1 all the way up n. All together raised to the power of 1 over n. But that's equal to this n cancel out. 2 to the power of half of n plus 1 times a1 all the way an to the power of 1 over n. So essentially we have this is less than or equal to that. Let me just write this down. So copy this down times all the way is less than or equal to this. K goes from 1 to n, 2 to the power k times ak. But what we want is we want this term, this summand, right? So we have to multiply, we have to get rid of this one. We multiply this over down here. So immediately we have raised to the power 1 over n is less than or equal to n times this one. N times 2 to the power of half of n plus 1. Sigma k from 1 to n. 2 to the power k times ak. But here we have n to the power over 2 to the power n. So we multiply by the same term. So n over 2 to n times a1 all the way to an to the power less than or equal to, copy this down, 2 to k, ak, n 2 to the half of n plus 1, multiply by n over 2 to the power n. Right? This n and this n cancel out. But the thing is that we have 2 to the power of half of n plus 1 plus n. That's not even a, right? That's, so combine those two terms plus n. Right? Maybe we put this n up here. We have 2n plus n, 3n. But that's not very nice because we cannot simplify this anymore. Right? So maybe if we don't have this half, maybe that'll look nicer. In other words, if we just somehow use 4 to the power of 2, 4 to the power of 3, all the way to 4 to the n, maybe that'll look nicer. Right? We can more easily simplify. Like I said, instead of using base 2, this time we use base 4. So this time we say 4 times a1 times 4 to the power of 2 times a2 all the way 4 to the power of n times an. We have this pattern. To the power of 1 over n is less than or equal to 4a1 plus 4 to the power of 2a2 all the way 4 to the power of n times an. That is sum k from 1 to n 4 to the power of k times ak. And at the same time, this is equal to what? So simplify 4 to the power of the sum of the 1 plus 2 all the way up to n. Again, half of n times n plus 1. We have the formula. Times a1 all the way to n. Raised to the power of 1 over n. Again, so we simplify again. So this power, n cancel out with this n. And 4 can be written as 2 to the power of 2. And 2 can cancel out with this 2. So in the end, we have 2 to the power of n plus 1 times a1 all the way to n to the power of 1 over n. So it's essentially we have this is less than or equal to that. Right? If we divide this term over to here, then we have a1 times 1 to less than or equal to n times 2 to the power of n plus 1. Sum k from 1 to n. 4 to the power of k, ak. And to satisfy this term, we multiply both sides by this term. Right? So we n over 2 to the power n times a1 times all the way n to the power 1 over n less than or equal to, copy down this, k from 1 to n, 4 to k times ak. We have n times 2 to the power of n plus 1 times n over 2 to the power of n. So we immediately have this n cancel out, 2 to the 2n plus 1. Right? So we get rid of this one, 2 times this term. And 2 to the power of 2n, that is 4 to the power of n, is the same thing. Right, simplify down to this. On top, we still have this sum. Okay, this n, gone. So we infinite sum on both sides. All right, this infinite sum denoted as S less than or equal to infinite sum of this finite sum. Right, maybe we just multiply this 2 over there. Right? With 2s we have less than or equal to infinite sum. Right, this 2 is gone. We have 4 to the power of n, a finite sum, k from 1 to n, 4 to the power of k times ak. All right, we have 2 sums, right? Inside sum and outside sum. And here we can, because here inside sum we're summing in regard to a k, so we fix n, k is changing, so maybe we can put this term down in here. Right? That is infinite sum. Right? This finite sum, 1, 2, and 4 to the power of k minus n times ak. Right, 2s is less than or equal to this. So we reached this inequality. 2s is less than or equal to this double sum. So first of all, we think of is that whether we can exchange the sums at all without any modifications. Right? So this somehow reminds me of the question that I did several years ago. I don't remember which exactly year. So essentially, it's about this summing of several numbers. So we start with denoted as perhaps A11 or B11, whatever. So A11 here. Then we stop right here. We start from the second row. We say, right, first index denotes the number of rows. Second index denotes the number of columns. So with second row, we have A21. It's still second row, but second column, we have A22. Right, we stop right here. Then we start from the third row. That's A31. Then A32. Then A33. Stop right here. Right? So on and so forth. So, for example, it's the nth row. So AN1, AN2, AN3. Right, so on and so forth. But we stop at ANN. Right, so on and so forth to infinity. Right. So why does this reminds me of this question that I did previously? So when you look at, this sum, right, think of it in this way. So there are essentially 2 ways of summing it. Right, so one way is to, of course, here we have every term is non-negative. I think that's a That may be probably a necessary condition, because otherwise it might not be true. But since every term is non-negative, so I think we're safe. So one way is to fix a row. Right? Fix the row n. We sum all those terms. Right? Then we sum another row. Then we add up all the rows. Right? That's one way of doing it. So way number one. Number one is first, like I said, row n, right? K is changing. K from 1, 2, 3 all the way up to n. So K is we sum with regard to K from 1 all the way up to n. Like I said, we fix the row number n. Right? Column is K, so A and K. Then we sum up all the rows here. So then we have to consider row number 1, number 2, number 3, all the way to n, all the way to infinity. So this time, row number is n changing, summing from 1 all the way up to infinity. N from 1 to infinity. That's the first way. So when you look at it, so it looks similar to this sum, right? K from n, then n from 1 to infinity. Right? But this A might be different from this A. It's just a notation. You could use B and K, whatever. But the second way is you fix a column. For example, I fixed column 3, or column K. Take 3, for example. So I fixed the number of columns. So 3 is fixed. But the number of row is changing, right? 3, 4, 5, and n plus 1 all the way. So, for example, I fix, like I said, first I change the row. I sum with regard to the rows. But the row, I don't start from row 1. I start from row 3. If I fix the column as number 3. If I fix the column as number k, I must sum from the row number k as well. Right? So first, let me just write down. N is the number of row. N this time is changing. So fix k, number of column. K is fixed. So like n, right, sum with regard to n. N start from 3, for example. Start from the number of k. Right? If it's k, we start from k. So column 3, we start from 3 as well. If it's column 4, we start from row number 4. So n always starts from k. Right? If it's k is equal to 3, we start from 3. K, if it's 2, we start from 2. So we start from k. Right? All the way to n, all the way to infinity. So to infinity. Then after you finish the calculation, the sum of each column, then you add up all the columns. Column 1, column 2, column 3, right, all the way. Right, then you say, right, then this time you start from k. K stands for sequence of columns. So column 1, 2, 3, 1 all the way to infinity. So essentially, we can rewrite this sum in this format. Right? So that is, you start from n, start from k to infinity. 4 to k minus n times ak. Then you say k from 1 to infinity. Right? So since the inside sum, right, sum with regard to k, or with regard to n, which means this time k is fixed. You pull out everything that has to do with k out from this sum. Right, for 4 to the k, we can pull out ak, pull out, times sum n from k to infinity. We only have 4 to the power of negative n. So that is essentially what? That is essentially that is essentially 1 over 4 plus 1 over 4 to the power k. 4 to the power k plus 1 all the way. Then that is, so first, there's a formula. All right, first term, 1 over 4 to the power of k. 1 minus the common ratio, that is 1 over 4. Right? That is, so 3 over 4, right, times 4 over 3. Right, 4 over 3. Times 1 over 4 to k. That is essentially 4 to the 1 over 3 times 4 to the k minus 1. Okay. Actually, I don't even need that. I just leave it as this one. So that is equal to k from 1 to infinity times 4k ak. So this infinite sum I already know. That is 4 times 4 times 4 to k minus k over 3. Right? But this 4 to the power k, 4 to the power negative k, they can just become 1. Right? They will become 1. So 4 over 3, I just pulled this one out. Right? K from 1 to infinity. AK. Now, since we're given that the sum, infinite sum, right, of AK, and the same thing is 1. So it's a constant, right? But that's 2s, not s. So 2s is less than or equal to 4 over 3, which means s can be no larger than 2/3. Right? So when do we reach the equal sign? Right? When do we reach equality? That's when. So remember. So what did I write previously? So that's when I rewrite. Remember, I write 4 times a1 times 4 to the power of 2 a2 all the way 4 to the power of n an, something like that, to the power of 1 over n. Right? So this am gm inequality, right, less than or equal to ... So equality holds when 4a1 equals 4 to the power to a2 all the way 4 to the power n an. So equal sign holds when we have those terms equal to each other. So if we just replace every term with term having in terms of a1 and sum them up, infinite sum equal to 1, right? That's a given condition, which means this infinite sum can be written as a1. I write down a1. a2 can be written as what? a1 over 4. Right? a3, so it equals 4 to the power of 3 times a3. So a3 has to be a1 over 4 to the power of 2. Right, all the way. So this is immediately a1, factor out. 1 plus 1 over 4 plus 1 over 4 square all the way. Right, this is easily, we have the formula. So first term 1 over 1 minus common ratio. 1 over 3 over 4. So times 4 over 3. 4 over 3. Right? That is given to be 1, infinite sum given to be 1. So immediately A1 is equal to 3 over 4. Right? So in this case, like I said, immediately A2 is equal to A1 over 4. A3, A1 over 4 to the power 2. So immediately 3 over 4 to the power 3. And the pattern is clear. So we reach the maximum value when, generally speaking, AN is equal to 3 over 4 to the power n, where n is equal to 1, 2, all the way.